Okay, so in this video, we're going to take a look at differentiating and integrating power series. So as of now, we've done a lot of manipulation with these power series, right? But one thing we can do, since really, if you think of the power series, it's just a polynomial of infinite degree, right? So we are able to actually integrate them using the power rule for integrals and differentiate them again using the power rule for derivatives, right? And that allows us to create even more functions for more power series for functions, right? So for example, right, we start off here again with the with our power series x to the n, right? 1 plus x squared plus x cubed, etc. Right? And we can find a power series for the function g of x, which is we'll define as f prime of x, which again using this is just a negative, well, it should be positive, right? 1 minus x squared, right? But then chain rule, derivative of negative 1, so the whole thing is positive 1 over 1 minus x squared. Now I can come up with a power series of this by taking the derivative of x to the n, right? And here the dx 1 plus x squared plus x cubed plus x to the fourth, etc. Right, and notice that the actual derivative itself is pretty straightforward, right? It's just application, repeated application of the power rule. So this becomes 0 plus 1 plus 2x plus 3x squared plus 4x cubed, etc. Right, and now I want to write this using sigma notation. Right, so here we could see the pattern that's arising, right? If we kind of, this is just 0, but if you notice here, the exponent and the coefficient, right? The coefficient is always one more than the exponent, right? Essentially the power. So n plus 1 x to the n, where n goes from 0 to infinity. And that is the power series for 1 minus x squared. Okay. Now, knowing the power series allows us to actually find the sum of certain series, right? As long as I can identify what function it is representing, right? So for example, let's say I wanted to find the sum of this series. All right, so one thing I can identify that it's of the form that I just calculated, right? Okay, where in this case my x is 1/3, right? And again, the interval of convergence is this, right? Okay, so here I can just plug that in. So we get 1 over 1 minus 1/3 squared. Oh, sorry, the whole thing squared. 1 over 2/3 squared, which is 9 over 4. Okay, so these are helpful when we can identify what function it represents to actually come up with a sum for the infinite series. All right, so now let's take a look at integrating. All right. Okay, so here, let's say that I want to find the power series for ln plus x. Okay, now one thing, so again, as of now, I just have that, always refer to this one, right? For now, where it converges when the absolute value of x is less than 1. Okay, all right, so here, first I want to identify that ln of 1 plus x is actually the integral of 1 over 1 plus x dx. All right. Okay. All right, so knowing that here, then we can use, again, let me rewrite this like this, right, in our power series form. So we're going to have the alternating series here, that is 1 minus x plus x squared minus x cubed plus x to the 4th, etc. dx. All right, and then taking the integral of that, I'm going to write the c up in front. So c plus x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. All right, so we see here now to identify the pattern, it's alternating. Our first one, so this one I'll start at n is equal to 1. I have an alternating one. If I started at n is equal to 1, I'll make sure to make the positive term first. I'll do that plus 1, so it starts off at an even number. And then the pattern is simply x to whatever power over n. All right. Okay, and here I can actually solve for that c. If I let x equal to 0, we get ln of 1, and notice that all these terms go to 0 in the series, right? If x is 0, this whole thing goes to 0, and we're left with c, and ln of 1 is 0. So we get 0 is equal to c. So we have our power series to be the sum -1 to the n plus 1 over x to the n over n. Okay, let's try one more here. So here I want to find a power series for the tangent inverse of x, right? And again, coming back to this one. Okay, so here we have, and first need to identify that the inverse tangent is the integral 1 over 1 plus x squared dx. All right, and again, that means the integral 1 over 1 minus negative x squared. Okay, which is the alternating series 1 minus x squared plus x to the 4th minus x to the 6th, etc. Right? So dx. Right? It'll be all the even values, alternating with all the even values. Taking the integral now for each individual term here, so we get c plus x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7th, etc. Right? And we see the pattern emerging. So now we have all the odd values here. Okay, so in order for me to do that, right, again, remember for odd values, so we have some so we're going to have odd values can be represented in this form, right? 2n always even. So if you add 1, the next one will always be odd. All right. And so this always has to match up with my exponent. All right. And it's alternating. So when n is 0, we get x to the 1 over 1, right? Okay. All right. And then here, so the alternating part, -1. First one is positive. So we're going to have, well, it starts off at 0, so we'll leave it at n. All right. So when it is 0, positive. When it's 1, negative, and it gives us to 3. Okay. And then we can solve for c again. If we let x be 0, the whole series goes to 0. So we get tangent inverse of 0 equals to c, or 0 equals to c. So now we have our tangent inverse of x. Okay. Okay, now one thing that I do want to just kind of mention here, the last thing here, is that you can mess with these counters, right, and it still represents the same series, right? So for example, I could let n be 1. Right now, in this case, I do have to adjust a couple things. The first term is positive, so this would have to be n plus 1. And in order to match up with the correct powers, I have to write it like this. All right, and then you see here now when n is 1, you get 2, you get 1 negative 1 squared, which is positive, and then up here you'll get 2 minus 1, which is 1. So you get the same pattern. All right, so just recognize that these are the same. All right, it's just a different representation.